Okay, so in this example we have a thin homogeneous bar, AB, which has a weight of W, and we're told this bar is released from rest at the position shown where theta is equal to 30 degrees. We're asked to assume all surfaces are smooth. Given this information, we're asked to determine the angular acceleration of the bar upon release, as well as the reaction forces on the bar at ends A and B. Okay, so since we're looking for angular acceleration and forces here, we know we're going to want to solve this problem using Newton's second law approach. And to this end, we're going to start by drawing a free-body diagram for this system. So what we'll have here is first of all the applied force F. We'll have a normal force acting at point A. We'll have the weight of the bar acting down, and we'll have a second normal force acting at point B. We know that the center of mass of this bar is able to translate in two directions, so we'll have some m times agx, and we'll have some m times agy, and we know this bar will be able to rotate, so we'll have some I about g times alpha as well. So now that we've completed drawing the free body diagram, we can move on to our kinetics equations. And so I can start by summing forces in the x direction. We know in this case that's going to equal the mass times acceleration at point G in the x, where of course G is the center of mass, and I'm using conventional xy coordinates. And if I work this out in this case, I'm going to have that F minus the normal force NB is going to equal the mass of the bar m times agx, and we can call that equation 1. I can do somewhat similar procedure here and sum forces in the y direction. So if I do that, sum forces in the y is going to equal m times agy. And if I work this out here, I'm going to have that Na minus the weight of the bar w is going to equal m times agy. We can call this equation 2. I can also sum moments about the center of mass. I'll set this equal to I about g times alpha, and to be consistent with my diagram, I'll sum moments here in a counterclockwise positive sense. And if I do this, I'm going to have, noting that this interior angle here is given to be this angle theta, I'll have first of all the NB, the normal force at B, creating a negative moment, and the moment arm in that case is going to be given by L over 2 times the cosine of the angle theta. I'll have the normal force at A creating a positive moment, and its moment arm is going to be L over 2 times the sine of the angle theta. And I'll have a negative moment coming from the applied force F, and its moment arm in this case is going to be L over 2 times the cosine of the angle theta. That's going to equal I about g for a thin bar, which is 1/12 times ml squared, and then we'll have that multiplying alpha, and we can call this equation 3. Now if we look at these three equations we get from kinetics analysis, we'll note that at this juncture we have, count them, 1, 2, 3, 4, 5 unknowns. And so we're going to need to turn to kinematics at this juncture and try to find some additional equations that can help us out. So to this end, I'm going to start by relating the acceleration of 2 points, and I'm going to choose 2 points that at first may not seem very sensical, but in fact will help us out immensely. And so I'm going to actually relate points A and B to start. This is not going to give us information directly about the acceleration of G, but we can use this to help ourselves out. So say the acceleration of A is equal to the acceleration of B plus the angular acceleration of the rod across R of A with respect to B, minus omega squared times R of A with respect to B. In this problem we're told the bar is released from rest, so this last term will go to 0. And so if I expand the remainder, what I'll have here is that AA in the I direction is going to equal AB, which we know to be in the J direction, plus alpha, which is in the K direction, cross R of A with respect to B. R of A with respect to the B in this case is going to be given by L times the sine of the angle theta in the I, plus L times the cosine of the angle theta in the J. If we go ahead and expand the right hand side here, we'll have AB in the J, K cross I is J, so I'll have plus alpha L sine theta in the J. K cross J is minus I, so I'll have minus alpha L times the cosine of the angle theta in the I direction. At this juncture I can pull out I and J components, so if I pull out the I components, I'll have that AA is equal to minus alpha L times the cosine of theta. We can call that equation 4. And if I pull out the J components, I'll have here that 0 is equal to AB plus alpha L times the sine of the angle theta, and we can call that equation 5. Now again, we didn't get anything directly useful here for computing AGX and AGY, but we did get, in this case, an equation related to AB, and this is going to be what's very useful for us. So what do I do now? Well, now I'm going to relate the acceleration of point G to the acceleration of one point we just found, which is B. And so in this case, I'll say AG is equal to AB plus the angular acceleration cross R of G with respect to B minus omega squared times R of G with respect to B. In this case, again, I'll note the bar's released from rest, so the last term will go to 0. And if I do my substitution now, I'll have AGX in the I plus AGY in the J is equal to AB, which we said was AB in the J, plus alpha in the K, cross R of G with respect to B, which will be L over 2 times the sine of the angle theta in the I, plus L over 2 times the cosine of the angle theta in the J. If we expand the right-hand side here, we'll have AB in the J, K cross I is J, so I'll have plus alpha L over 2 times the sine of the angle theta in the J. K cross J is minus I, so I'll have minus alpha L over 2 times the cosine of theta in the I. We can now pull off the I and J components respectively. So if I do that, let me give myself a little more space here. In the I direction, we'll have that AGX is equal to minus alpha L over 2 times the cosine of the angle theta. Let's call that equation 6. And in the J direction, we'll have that AGY is equal to AB plus alpha L over 2 times the sine of the angle theta. Let me clean up that 2, and we can call this equation 7. Now, if you'll note, we've added 4 additional equations to what we had from kinematics, or excuse me, from what we had with kinetics, and we've added here very few additional unknowns, and so the end result is we now have 7 equations, 7 unknowns, which you can use to find all of the wanted quantities in this problem statement. So from here on out, the problem's simply algebra, and I know it's a problem you can handle. So I'll simply wish you the best of luck. Take care, everyone.